Hi and welcome to this section where we would like to look at functions of complex variables. So the assumption here is that you have already gone through a course on complex numbers or complex variables and are well familiar with most of the basics. Okay, in here we are going to deal with it's quite theoretical. In here we are going to look at a number of theorems and just like the course outline depicts, we are going to look at a number of theorems and some calculus to involve in these complex variables here. So okay, let's just get straight away into what we are going to look at today. We are going to say that a function of a complex variable is a mapping, okay, is a mapping, let us say f of z, is a mapping f, okay, which maps a complex number z onto another complex number w, okay. So we map specifically a complex number z, which we can maybe write as x plus iy, okay, to another unique complex number w, which we can maybe write as u plus iv, okay, where x and u are the real parts. This is the real part of z, and this is the real part of w, and then v is the imaginary part of w, and y is the imaginary part of z, okay. So a function is a mapping or a relation which maps, okay, a complex number z onto a unique complex number w. So maybe what we need to note here is that if z is a function of x and y, you can see here z is a function of x and y, and so w, okay, which has u and iv, is going to have u, which is also going to be a function of x and y, and v, which will also be a function of x and y, okay. Yeah, so we can write as this actually as u, if we want to write it explicitly, the function of x and y, plus v, the function of x and y, iv here, okay. So let us look at an example. So the first example that we are going to see here is that what if we have a function here f of z given as z squared, okay. So we can say maybe we can let our z equals to x plus iy, it's a complex number, then f of z, as in our function f on z is going to be f on x plus iy, which is going to be x plus iy everything squared, okay. So if we expand this, we have x plus iy, x plus iy, and so we have x squared plus 2xy, x squared plus 2xyi, okay, and then plus I squared y. So this goes to x squared, I squared is -1, okay, because we know I is square root of -1, therefore I squared is -1. So we have minus squared, then plus I 2xy. Alright, okay. So so we can as well say now our f of z here gives us this, where we have the real part and here the imaginary part. So here we can say that this is our uxy, and then this is our v, which is a function also of x and y. So that is just an example of a function. We are just writing here an example of a function of a complex variable. So the goal the goal of the function, the goal of having complex functions is to perform, perhaps for this course here, is to perform integral and differential calculus. Okay, integral and differential calculus. Okay, and also to do some other analysis, we shall see. Okay, so now that we have that goal in mind, let us go to the next thing. And like I said, it is going to be quite theoretical, so we are going to have some definitions, some theorems, and so on and so on. So the very first definition of interest here is the definition of what we call a holomorphic function. Holomorphic function. Okay, so how do we describe a holomorphic function? Well, we say that a function f of z, okay, is holomorphic in a region R, is holomorphic in a region R of the complex plane. Okay, perhaps I can pause here and just try to explain something. You know, when we have a complex number, okay, our complex number, its region of the region in which it is defined is a plane, okay, because it is in 2D. We have, if this is z, which is equal to let's say x plus iy, we have the real part, okay, of z, the real part, okay, which is the x, okay, this is the real part here, which is the x, and then here we have the y, which is the imaginary part of z. Okay, so it is defined in a plane. This one here, it is 2D. Okay, so that is why we say that the function f of z is holomorphic in a region R of the complex plane. Okay, if it has a unique, derivative, at every point, in R. Okay, so let us assume that it was maybe our region of interest was a circle here. So we would say that z here is holomorphic. Okay, if within this region of interest, which we are saying a circle of a certain radius, if it has a unique derivative at every point in R, okay, at every point in R. Perhaps what I don't want to go so much into, because that is so much of the pure mathematicians and so on. Here we're getting the idea is that if you tell me every point in R, are you also going to include the boundary points, or are you not going to include the boundary points, and so on? For now I cannot answer that, okay? But let it just be at the back of our mind that in the region here we could as well be thinking about the boundary as well, okay? But okay, for now let us just say our function is holomorphic in a region R of the complex plane if it has a unique derivative at every point in there. So we talk about that it is having a unique derivative, but do we know what a derivative of a complex number is? Well, not yet. Perhaps you know, but I have not yet discussed it here. So let us define here what is the derivative of a complex function. What is the derivative of a complex function? Well, I want us to recall something here. Okay? For normal functions, a real valued function, if you had a real valued function, for our real valued function f of x, okay, we say that it has a derivative, it is differentiable, it has a derivative at x equals to a if, okay, this limit exists, if this limit, okay, of f of a plus delta x minus f of a all over delta x as delta x approaches 0, if this limit does what? Exists. So we say that our real valued function f of x is differentiable at x equals to a if this limit exists and is unique, okay, and is unique. In other words, okay, we are going to check, okay, if you remember, we will check that the limit as you know, we approach 0 from the left, okay, of f of a plus delta x minus f of a all over delta x should be equal to the right hand limit, i.e. as you approach, as delta x approaches 0 from the right, okay, f of a plus delta x minus f of x, minus f of a all over delta x, okay. So that is what we are interested in, that the left hand limit a1 of first the limit exists and the left hand limit is equals to the right hand limit, okay. That is for real valued functions. So now the idea is more or less the same here for what is it, our complex valued functions. And what are we going to say? We are going to say that for our complex valued function, okay, let's say our complex valued function, let's just call it f of z, we are going to say that the derivative, okay, the derivative, which we are going to denote as f dash fz, we are going to define it if, okay, this is still notation, we are differentiating f of z with respect to z is going to be equal to the limit, if this limit actually exists, as delta z approaches 0 of what is it, okay, of f of z plus delta z minus f of z all over delta z, okay. So if you know this, if this derivative is defined as that limit, okay, so that if this limit actually exists, then the derivative here is there. And also for this one here, the derivative as delta z approaches, you know, 0 should be equal from whatever direction. Only that since we said that the complex numbers here are defined in a plane, it does not make sense for us to say that as delta z approaches 0 either from the left or from the right. No, that we can only say from the left or from the right, because for that real valued function f of x, we simply had the values here f of x and then you had here x, okay. So we are approaching x, okay. In other words, our delta x was approaching 0. You can either approach it through positive values or you can through negative values, as in it is just on the number line. You can just represent this on the number line, so you can approach 0 either from that side or from that side. But it is quite different here for our complex numbers because it is defined in the plane. Therefore there are many, the point here is that there are multiple directions at which you can maybe approach your number, if that is z, okay. There are many directions at which you can maybe say delta z is approaching 0, okay. So, by the way, please note, I am using these terms, throwing them just around, basing on the idea that you know, you have an idea what it means when I say, you understand when I say that as we approach x, okay, as I'm approaching x, it ideally means that the change in x is approaching 0. So if I have a complex number here z, as I am approaching z, essentially delta z is approaching 0. Okay, only that here we can approach x here from just two directions, either from this side or from that side. Okay, that is why we talk about the left hand limit or the right hand limit. However, here we can approach z from all multiple directions, left, right, center, diagonally, north, northwest, and so on. So it is quite challenging, but then that also tells us that the definition of the derivative of a complex valued function is much more strict. Because whatever direction you approach this complex number z, or that the limit must be unique. Okay, so what else can I explain here? Yeah, all those derivatives must exist and must be unique. That means that this derivative here of a complex valued function is quite stringent. Okay, so in other words, later on we will find that you can actually find a complex valued function which is made up of functions which, if they were real valued functions, they are differentiable, and yet if it is in the complex, if they are complex valued, they are not differentiable. Anyhow, let us look at an example here. So what example can we look at here? There's an example here. We can look at an example here. Let's see if we have f of z given as z cubed. Okay, so we say f dash of z is the same as dash with respect to z, which is the limit as delta z approaches 0 of f of z plus delta z minus f of z all over delta z. Okay, which is limit as delta z approaches 0. What is f of z? F of z plus delta z is going to be that cubed, then minus z cubed over delta z. So what is this going to be? It is going to be limit as delta z approaches 0, z cubed, okay, plus 3z squared delta z plus 3z delta z squared plus cubed. Okay, then minus z cubed, let's not forget that, over delta z. So this is going to be the limit as delta z approaches 0. So a few terms here cancel. We can cancel this term and that term. So we have 3z squared delta z plus 3z delta z squared 1 2, and then we have delta z cubed, everything divided by delta z. So we have limit as delta z approaches 0. We can divide through by delta z, so we have 3z squared plus 3z delta z plus delta z squared. So as delta z approaches 0, this is going to approach 0, and this one is even going to approach 0 much faster, okay, because you're even squaring it. Therefore what we have here is just 3z squared as our derivative of that. Okay, yeah, pretty simple example, and I hope you have, you get the idea here. So this limit exists unless we have reason to show that it does not, whatever direction we approach z from is not, that the limit is not unique. Unless we can show that, then we can say that therefore this f of z is holomorphic. Okay, once again, what did we say holomorphic function is? We said that a function is holomorphic in the region R of the complex plane if it has a unique derivative at every point in R. So we have found that with the derivative, which is defined as the limit, you know, of this, and we have found it here, okay? Therefore we see that, you know, this function here is holomorphic. Okay, now I will, maybe to make much more sense, I will show you one which is not holomorphic, therefore you will easily see it. So in general, okay, we are going to say that our function f of z, which is given as z to the n, is holomorphic. In other words, functions of this form, okay, are holomorphic, okay, and we have that the derivative here is given by the usual power rule, n z to the n minus 1, okay, where n is an integer, okay, n is what? An integer, positive integer, okay. So yeah, that is it. Maybe next we look at an example of a function which is not holomorphic, and then we see what happens, okay.